Bungalow Bill here, and welcome back to From the Depths. So since getting 1,000 subscribers, I've decided to update my computer again, and as you can see, From the Depths is much more realistic than before. Unfortunately, I found that the physics is also more realistic, and it has been causing me some trauma. However, I will rebuild this at some point and get more in tune with the new physics engine that I'm dealing with. In the meantime, I'm going to be taking a look at how effective different angles actually are, as well as different blocks actually are at dealing with kinetic damage, because I'm going to be retrofitting a tank soon, and I want to have at least some idea of what kind of decisions I'm going to be making. Now, I'm going to be doing this in a horizontal orientation because of YouTube. Usually I would have my paper turned this way, but it wouldn't work that well unless you really want to watch it on your iPhones, or whatever phone you have, which I'm sure many of you do. So, okay, how does kinetic damage work? As far as I can tell from what I looked up, let's say you have a block at some angle. This is going to be a 4-meter beam slope coming out of the paper, so we'll pretend that's a 45-degree triangle. It's got a right angle, and the other two angles are the same. Coming directly into it is a kinetic projectile. The kinetic projectile makes some angle with the normal coming off the triangle. In math terms, this just means that it's 90 degrees to the face of the triangle, or perpendicular or orthogonal, depending on what language you want to use. And the damage is multiplied by the cosine of the angle between the direction the projectile is going with and this normal. In this case, that's going to be 45 degrees. And I know that I have people of many different age brackets, and this isn't a math channel, so I'm going to try to keep this one relatively low in the math spectrum, although we will be doing a small amount of calculus, and there's some things fairly fundamental to that I'm just going to sort of gloss over, and they'll either make sense to you or they won't, but I promise that they'll work. But this is going to be, high school level. My math skills have degraded a lot since being in college a long time ago, so it's not like mine are that sharp anyway. So just to refresh everyone in case you don't remember, in trigonometry class in high school, usually people learn this mnemonic, SOHCAHTOA. So you would just write SOHCAHTOA. And what that reminds people of is that the sine of the sine of an angle in a right triangle, or just, the sine in general, the sine function is defined outside of that, is going to be the ratio of the opposite side to the hypotenuse, the long side of the triangle. The cosine will be the ratio of the adjacent side to the hypotenuse, and the tangent will be the ratio of the opposite side over the adjacent. So in this case, we've got a 45-degree angle. The cosine of 45 will be the ratio of the side lengths in a right triangle. So adjacent, for a beam slope, this is going to be 1. The hypotenuse, well, with the distance formula, that'll be the square root of the sum 1 squared plus 1 squared. So the hypotenuse is going to be the square root of 2. So we'll have that cosine of 45 equals 1 over the square root of 2. For me to be able to roughly evaluate this on pencil and paper, I need to remove the radical from the denominator. So I'll multiply the top and bottom by the square root of 2 and get root 2 over 2. And I know that this is give or take 0.7. The square root of 2 is a little bit more than 1.4. It's like about 1.41. So this is about 0.707. And so we'll deal about 70% kinetic damage in this configuration. Something that I do remember seeing at some point in the patch notes, this might be a false memory because I can't find any information that other people said about it where I see references to kinetic damage calculations, is that I thought, because of how effective wedges are, and we'll see that in a second, at mitigating kinetic damage, that, well, something was done to change the damage calculations so that we're not just using this angle anymore. Hopefully that's just a false memory. I couldn't find anything about it, so I'm omitting it. I'm also omitting bounces. Shells can bounce at some point, and that further reduces damage. But in my experience, big shells don't bounce, or just decent kinetic shells in general don't bounce, so I'm not really that worried about it. So let's take a look at another case. And let's say we have a wedge. This is a very poorly drawn wedge. So in the direction that it's facing, it's 4 meters long, 1 meter tall, and from where I've cut it in half here, it's half a meter tall. And we'll have some projectile come in and hit it. And we'll take the normal here, so we're looking for the cosine of this angle. So here, these two things are parallel, which means that this angle and this angle are the same. This is a right angle, and the angles of a triangle have to sum up to 180, which means that these two have to sum up to 90. Since I just drew the normal off of this, I know that these two angles sum up to 90. That means that this angle and this angle have to be the same. So I'm going to take the cosine of this angle, which is the adjacent 1/2 over the hypotenuse. If I use the distance formula, it'll be the square root of the sum 4 squared plus 1/2 squared, so that's the square root of 16.25. It's going to be ever so slightly higher than 4. I'm just saying this is approximately 4. If you're interested in the exact numbers that come out of this, you can always, figure out what this actually is. So I'm going to say that the factor applied to the damage dealt is approximately equal to 1/2 over 4, which is equal to 1/8. And that's a lot less than 70%. That's a very massive damage reduction. So you can see why this might be interesting, because these two have the same volume factor. They occupy half the space because they're both triangles. Where you could put one of these, well, you could put 4 of these, which means that, and I'm referring to the fact that these have to be front towards the enemy. So if you're punching through one of these, you'd have to punch through 4 of these. Naturally, it leaves a bigger gap, but against kinetics, you're often worried about the shell just going all the way through your vehicle. That's your concern, rather than them sandblasting the armor. If they're sandblasting the armor, this is just a lot better. But, well, even if you have 4 times as many of these as these, the ratio is still in your favor as long as you're meeting this angle, because the comparison would be, is 4 times 1 over 8 better than 0.7? Well, the answer is yes. It comes out to a half. You're still getting through fewer of these than you are of these. Now, if you're fighting a long ship, it might be shooting some shells in from the side. Maybe your craft isn't always pointing towards the front. Maybe you're fighting more than one enemy vehicle. You might not always get the best case scenario, but this number, very, very good. So this is actually going to be justified in some cases. You might also be concerned about other damage types, because, a piercing pack doesn't care. Fragments from a frag shell, I have no idea. They do kinetic damage, so I imagine they care, but who knows what angle they're spraying at. So we're going to use this paper for more identities in the future, so I'll keep it. But the actual thing that I'm really interested in, and the reason we're on pencil and paper, we will return to the digital space, but the reason we're on pencil and paper now is because I am interested in this shape. It's supposed to be a circle. So this is the pole, my favorite beam. And I want to know, is this better than a wedge at kinetic damage reduction? So, all right, how do we calculate this? And the scenario that I'm going to be interested in, this pole is going to function exactly the same no matter where the enemy is shooting from. So there's no best case, there's no worst case. I'm going to say that we're taking projectiles in evenly through space and they're all going in the same direction. It doesn't matter where they're coming from, as it's a circle, it's going to behave exactly the same. And at each particular point where a projectile is coming in, I'm going to take the damage at that point. We'll say maybe I break the circle up into a lot of little pieces based on height. So for each of these pieces, I'll multiply how tall they are by the damage factor at that point. I'll sum them all up, and then I'll divide it by the total length, and that'll give me the mean damage reduction of this circle. The first thing to do is figure out how to calculate the damage reduction at a given point. And something fun, always that's just fun mathematically, is your intuition. Is this better or worse than a beam slope at 45 degrees in terms of mean damage reduction? Now, my intuition says that, let's say I take a 45-degree line, I think that all of the stuff here is going to be so bad that it doesn't make up for how good the stuff here is. The reason I say that is because if you take a cosine function and kind of plot it, it's very flat for a very long time up here before it really starts to come down. And it doesn't get to 0 until here. And it tends to be pretty, it's pretty good compared to a straight line. So I'm going to tend to think that we get very good damage reduction here, but given how bad the damage reduction here is, it's not going to make up for it. So my money is somewhere between, I don't know, like 0.75 and 0.85. We'll have to see exactly how well it does, but that would be my bet. So at some point here, we have a projectile coming in, and then we have the normal where it's intercepting. And what we need is the cosine of this angle. Well, this is parallel to this x-axis that I drew, so we'll transfer this angle down here, and we'll just call it theta. So all that we're going to say is that at a point, the damage reduction is going to be cosine theta. We'll figure out what that means a little bit later. And now, what's the height? Well, it's not along the circle, it's along this axis, and I'm going to call these x and y. So it's going to be just a small change in y. I don't know how many of these divisions I'm making, so we'll do it like that. And I want to sum all of them up, so I'm going to put a squiggly s next to it for sum. So I'm going to say that my mean damage reduction is the sum, and I'm only going to sum the top half. And in particular, even though this is supposed to be a pole, I'm going to make this 1 meter in radius, so it's actually twice as big as a pole. So I'm going to be summing from 0 to 1. And then I'm going to be dividing it by that distance, which is 1. And I don't have to do the bottom because the bottom's the same. So it'll just be this. It'll be, this from 0 to 1. I'm going to omit these in the future to save a little bit of time, and divided by 1. So unfortunately for me, y and theta are different. So I can't just move along the y-axis. They have a correlation, but I don't know what that correlation is yet, which prevents me from summing all of these up in a convenient way. So if I take the identity that I had here before, what I'm going to get is that cosine theta is going to be my x-coordinate, and sine theta is going to be my y-coordinate. And if I take the distance formula for a circle, I'm also going to have that the square root of x squared plus y squared equals 1, or more simply just x squared plus y squared equals 1 squared. So, and the cosine of theta is x, I need to get it in terms of y. So we'll look over here. We have y squared equals 1 minus x squared. And that implies that y equals plus or minus the square root of 1 minus x squared. I'm only working in positive y and positive x because I'm in this quadrant. So it's just going to be the positive side. We don't have to worry about the negative side. I wanted to do that in the opposite direction, but fortunately, this is incredibly symmetric, so the opposite is also true, that x equals the square root of 1 minus y squared. I don't know how math teachers do this. I find it difficult to talk and do math at the same time. Often I find it difficult to do math at all, but that's its own matter. So what this is going to give me is the integral of 1 minus y squared dy. This is pretty famous, actually. If you've done calculus, you've done this integral. And in particular, I can't integrate this. This is actually halfway to the form that you'd normally integrate this in. This is the form that's often presented to you as showing people how to use substitution, because I need to use a different variable other than this one, and this is a good hint because I should know that this is somehow related to a circle, and obviously this integral would be far better to do in some sort of polar form. So let's not do this. Instead, let's figure out how dy is related to theta. And what I do know is that as I turn theta, so as I make a change in theta, the amount of y that changes is going to change. So here it's going to change quite fast. Here it's going to change quite slow. So my intuition here tells me that it's 1 to 1 here, and it's 1 to 0 here. And it does that along an arc of 0 to pi over 2. My intuition tells me that the relationship is going to be have a ratio of cosine of theta, so that the change in y is going to be the change in theta times cosine theta. However, I need to prove that because it's not enough to just think something is true, I have to know that it's true. Let's put my equal sign in there. So the way that I'm going to do that is I'm just going to say that there is some other variable t. And we'll make this really simple. We'll say that theta of t equals t. So now I have a parametric equation, and I'm driving theta in terms of time. And this is important because I need to take a derivative of both of these functions with respect to something. So in this case, where I have sine theta equals y, well, I'm going to derive both sides with respect to t. So this is one of the very fundamental things that I am not going to prove along with some integrals. I get, in this case, the derivative of sine is cosine. So I have cosine of theta. Now I have to take the chain rule where if you have a function, it's not just the derivative of the function, it's the derivative of the container of the function. So that's going to be d theta over dt. And that's going to equal the change in y with respect to the change in time. Now, I'm a charlatan, so I can just cross these both out, and I get cosine theta d theta equals dy. I'm going to go in and substitute that in here, and that's going to give me cosine theta times cosine theta, so cosine theta squared, d theta. So this I can work with. And the reason I can work with it is that I know how to integrate sine functions that aren't squared, and I know how to reduce the power of a sine function. Of course, I don't remember exactly how to reduce the power of a sine function. In trig, I was always bad at remembering identities, so I know that there's a relationship between the cosine squared theta and cosine of theta, but I don't remember exactly what it is. So the way I'm going to address this is I'm going to draw a circle. And I'll draw a set of axes on the circle as well. And I'm going to draw a few angles. So here I'm going to have alpha, here I'm going to have beta, and here I'm going to have the same angle beta. And I'm going to introduce 4 points, and I'm going to use the same letters except in a different alphabet, just to make it confusing. So I have A, B, C, and D. And what I know here is that the distance between A and C is the distance between D and B. So that would be like so. And I also know the coordinates of all of these points, so that I can actually write out the distance formula in each case. So I know that A is going to equal, and I like using brackets here to denote vectors. Some people like to use parentheses or square brackets. I like angle brackets because I use parentheses and square brackets in functions, and I'm going to be using both here later, or rather to, not in functions, but to denote groups. So A is going to be cosine of, and now because we're going in the opposite direction, it's going to be cosine of negative beta, and it's going to be sine of negative beta. I'm not writing this minus sign in because sine is an odd function, which means the sine of negative beta is equal to negative sine beta. Cosine is an even function, which means cosine of negative beta is equal to cosine of beta, so we'll just write that out like that. B is particularly simple. It's just x. These are x and y coordinates. I should label my axes. I'm using the same axes in all of these. C is going to equal, that's a particularly bad bracket, cosine alpha, sine alpha, and similarly D is going to equal, well, now it's going to be the sum, cosine of alpha plus beta, and we have the sine of alpha plus beta. So let's look at AC first. And I'll just start cluttering this up a little bit. So we'll take the distance function again, where I take the difference of the x coordinates, square them, sum that up with the difference of the y coordinates, square them, and take the square root of the whole thing. So for AC, that's going to be cosine of beta minus cosine of alpha, and it doesn't matter which direction the difference is in because square is an even function. So if I multiply the inside by -1, it doesn't make the tiniest bit of difference. And then on the other side, well, I'll have negative sine beta, and I'll have minus sine alpha squared, and taking the square root of the entire thing. So now I've got to distribute my fractions, and the way that I'm going to do that, some people remember FOIL of the first outer inner last. If I have a plus b squared, and squares look like this, I have a squared plus b squared plus ab plus ab. So I'll do that here. So that's going to give me cosine squared beta minus 2 cosine alpha cosine beta plus cosine squared alpha. And I'll get a very similar thing here, except I've got these two minus signs, So I'll get plus sine squared beta plus 2 sine alpha sine beta plus sine squared alpha, and taking the square root of the entire thing. Now, this is a lot of junk to deal with, but fortunately for my distance formula, given that I'm working on a unit circle here, which is why all this stuff is going to work, so these are all length 1, and I know that the x and y coordinates on any of these look like this, well, I know that cosine squared beta plus sine squared beta equals 1. Similarly, I know that cosine squared alpha plus sine squared alpha is equal to 1. So I'm going to be able to take these two out, convert those into 1. I'm going to be able to take these two out and convert them into 1. So what that's going to leave me with is 2, and since this one's positive, I'll put it in front, plus 2 sine alpha sine beta minus 2 cosine alpha cosine beta. And that's all to the 1/2. All right, let's take BD. That one's a little bit easier. And again, these are equal. So this is equal to the previous line that I have as well. So B is just 1, 0, which makes things really easy. So I have 1 minus cosine alpha plus beta squared, and then plus, well, all that I've got is 0 minus sine alpha plus beta, so I'll just write that out as sine squared alpha plus beta, and that's all to the 1/2. And I know that that's equal to 1 minus 2 cosine alpha plus beta, plus cosine squared alpha plus beta, plus sine squared alpha plus beta, all to the 1/2. And I can do the same trick that I did before. I almost moved my 2 outside of my brackets. That would have been very illegal because I'm adding this 1 that I took here. So I have 2 minus 2 cosine of alpha plus beta. And I know that that's equal to this. So I'm going to square both sides, subtract the 2, and divide by 2. So that's going to leave me with sine alpha sine beta minus cosine alpha cosine beta is going to be equal to cosine. Let me not drop the negative sign. I almost did that there. That would have ruined all of my plans. Cosine alpha plus beta. So I'm going to do two things here. I'm going to say that in this case, alpha equals beta, and I'm going to flip the signs. So here I'm going to have cosine squared, because now I've got cosine alpha times cosine alpha. So I've got cosine squared alpha, and I'm flipping the signs, so I've got minus sine squared alpha equals, again flipping the signs, cosine of 2 alpha. Now I'm almost there, and what I'm going to use again, as I've used many times here, is that cosine squared plus sine squared equals 1, or sine squared equals 1 minus cosine squared. So I'm going to have cosine squared minus 1 minus cosine squared, or 2 cosine squared alpha minus 1 equals cosine 2 alpha. And finally, fixing this for just cosine squared alpha equals cosine 2 alpha plus 1 over 2. So let's get back here. I now have that this is the integral of cosine 2 alpha minus 1 over 2 d theta. And I can finally work with this. So I'm not sure why I wrote another integral. I don't need another integral. We can just integrate this. Let's get rid of this guy. So I know that the derivative of sine is cosine, and integrals and derivatives are opposites, so I'll have sine 2 alpha. I'm really in my alpha space. Okay, let's go back into theta land. This is the way our substitution used to work. So I've got sine 2 theta. Well, the derivative of sine 2 theta is going to be 2 cosine 2 theta. So I'll have sine 2 theta over 4. This will properly get me into that place. This is where you get yourself in trouble with math as well. I'm particularly in the habit of doing this. The integral of a constant being that variable times that constant, so theta over 2, plus c. However, this is a bounded integral, so c doesn't matter because I'm taking the upper bound and subtracting the lower bound from it. I'm not doing this from 0 to 1. I'm evaluating this from theta equals 0 to theta equals pi over 2. Normally, if you were asked to integrate this, once you get here, you have to substitute y back in. There's no reason for me to substitute y back in and then evaluate. You actually wind up getting an arcsine function in here. So this is not 1, like it would be if I was doing y. This is pi over 2. So what I do is I evaluate the upper bound and then subtract the evaluation of the lower bound from it. However, sine of 0 is 0, and 0 over 2 is 0, so this lower bound is going to evaluate to 0. Additionally, for the upper bound, sine of pi is 0, so this is nothing in either case, and I'm just left with this. So my mean damage factor for my pole is pi over 4. But I need to know what pi over 4 is, and I left my calculator at home. Actually, in particular, I'm actually recording on my calculator right now. So, OBS. It's definitely not an iPhone that's balanced on a level that's balanced on a piano bench and has a laptop sitting on top of it so everything doesn't fall over. So, I've got 3.14 over 4. Now, I know that pi is approximately equal to 3.2, so I'm going to say that's good enough, and I've got 3.2 over 4, which is 0.8. So, comparing these back to my previous ones, these two aren't so far off. There are always other factors into consideration. You can have damage stacking for beam slopes. You cannot have damage stacking for poles. Not damage stacking, armor stacking. So, if I have a beam slope, well, I can put armor blocks behind this. And now, if this is heavy armor, instead of an AC of 60, that's going to go to 72. Against kinetic damage, this shouldn't matter because anyone who's trying to punch through heavy armor is going to have an armor piercing value of 72, but it might be very important against frag damage, HE damage. It could be useful against kinetic CWAS that's pointed against your craft. Thump damage. There's any number of stuff where you would care about this. Whereas for a pole, well, no matter how I do this, because air gaps, and I think now armor stacking treat this as a perfect circle. There's an infinitesimal place where these two touch. No matter how you try to throw a line, you have a 0% chance of getting it right through that tangent spot. As to whether or not the calculations that From the Depths actually does allows for some tolerance where the line actually gets the armor stacking value, I don't know. But I would just go ahead and consider that no matter how you align this and how you stack things up around it, it has an air gap on every single side, which has some use in constrained spaces, but it gets armor stacking from no side. So with this out of the way, I'm going to go into Excel, do a plot of the different armor values that you get against angles, and then show where the different beams line up on that plot. So I'll be back with you on the comforting online space in a moment. You might be wondering why I put myself through all of that, and the answer is I had to know. The other question is, well, why did I put you through all of that? It's because I had to go through all of that as well, so of course you do as well. If you're still here, you get rewarded with an Excel spreadsheet. So this also has the poll for apparently sabot heads actually take 3/4 of the angle. I'm not going to go through all of the math again. You can do a very similar thing that I did to get to this answer. Instead, you're going to be integrating the cosine of theta times the cosine of 3/4 of theta. It's a little bit trickier. There are other trigonometric identities for products of cosine, and the way that you get there is you not only have to get to the sum of cosine, or it's the sum of angles identity for cosine, you also have to get to the difference. And then once you take the two of those, you can take the difference between them, pull out the product of cosines, and you can actually move somewhere with that. It's a bit longer and more involved. I'm not going to go through all of that again. But this is to say, I said that the poll for normal kinetic, so normal kinetic is heavy head and armor piercing capped. I said it was roughly 0.8. It's 0.785. Good enough for government work. And I said that the wedge was about 1/8, which is about 0.125. It's 0.124. That's way closer than you would ever really need. So here, at a variety of angles from 0 to 90 degrees, I have the damage factor for armor piercing capped or heavy head, and then I have the damage factor for sabot. And you can look at that here as well, that sabot ends at about 0.38, whereas everything else ends at about 0. And I also took the difference between the two. And the difference between the two shows what percentage of damage you're losing by the difference in the formula, the calculations for the formula. So what this really reinforces to me is on a lot of ships where I use AP capped heads, this is why they struggle so much against a lot of the Grey Talons builds that have these forward-facing 4-meter wedges that I'm hitting really at pretty much the worst angle all the time. If I was using sabot, I could punch straight through those, through the other side of the craft. This is definitely one making me consider I'm probably going to use solid shot a lot more than I do currently. I had never actually looked at this before, and I really don't think that what you get from payloads from AP shells is actually worth this difference. I think there's still a time and a place for AP shells, But something that I have with them a lot is it's really hard to get them to detonate in a place that's actually helpful. You often have to tune the depths or the weapons that you're using for specific ships. Instead, well, I could just use higher fire rate sabot shells that deal about the same amount of kinetic damage but don't have a payload, or at least have the same firepower but don't have a payload, and are more consistent against the larger variety of targets and don't suffer the way that they do against the Grey Talons. And so if I look, well, once I'm facing sabot, a pole and a beam slope, they're not so different. The difference between a 4-meter slope, which I don't think you'd ever have any reason to use, is pretty noticeable. So for me, the main difference is whether I want to use a wedge or a pole. And for both an air gap and potentially for kinetic damage resistance. There's a few things going on here as well. That in From the Depths, if you have a block, an air gap, and then another block, you punch through one. As soon as it surfaces into the block, it'll take the damage factor. As soon as it exits, it'll reset. And then when it surfaces into another one, it'll calculate the angle. So if you back a 4-meter wedge by solid blocks, that's actually really good if you have the room to do it. I don't know if I'm going to have the room to do it in my tank, but I may start doing this on a lot of craft, that I have enough room for this sort of thing. I might have one layer of 4-meter wedges backed by other armor, which would give me a very significant bonus to my ability to defeat a single large kinetic round. As far as my craft, I'm going to have to evaluate whether or not I actually have the room to do that. If I do have the room to do that, I'm going to do it. If I don't have the room to do it, I'm just going to use a pole for my air gap. This is an issue that you always face when retrofitting craft, that you only have a certain amount of room. If you're not retrofitting a vehicle, you might as well just build it the way that you want. And at least for front-siders, where it's not that painful to put these wedges in, I think I'm always going to use one layer of them. I don't think I'm going to stack wedge, 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 but I think for front-siders at this point, I'm always going to have at least one layer of 4-meter wedges. And for weapons, if I'm using Kinetic, I'm either going to be using heavy heads for CWIS, or I'm going to be using sabot for actual damage to enemy vehicles, and I'm going to stop using the armor-piercing capped heads almost entirely. So that's all that I have for this episode soon. You might be wondering, this episode soon? No, this is all that I have for this episode. So you might be wondering, what am I actually going to play From the Depths? Well, I am going to actually go and retrofit that vehicle and then finish my carrier, and then hopefully get back into the Ruler of Steel. And then I have been going on a custom campaign kick. I want to actually do some more core From the Depths gameplay. And there's a few weird things that I want to do as well, some very degenerate things. We'll see if I get that far or not. Anyway, I've dragged this episode on far, far longer than it needed to go. So those of you who made it all the way to the end, I hope you enjoyed watching, and I'll see you in the future.